Bismillah ar-Rahman ar-Rahim. Chapter 4, Aromatic Compounds. Aromatic compounds are compounds found in nature like bitter almonds, لوز المر, contain benzaldehyde, a benzene derivative compound derivative from benzene called benzaldehyde. The simplest compound of the aromatic compounds or arenes is benzene. The structure of benzene is unique. Benzene is a cycle with 6 carbons and 3 double bonds. These 3 double bonds are not localized, they are delocalized. Delocalized means there is a continuous movement of the double bond between 2 different carbons always. This delocalization result in 2 resonance structures, resonance hybrid structures called Kikuli structures. All carbon-carbon bonds in benzene are with equal length and strength. They are 1 sigma and half pi. This is the first fact about benzene. The second fact about benzene reacts mainly by substitution reaction. The hybridization of benzene is sp2 hybridization, and there is a sideway overlap between each 2 carbon to form a double bond. The 3 double bonds could be delocalized around the 6 carbon of benzene. So the correct symbol for benzene is not Kikuli 1 or Kikuli 2 hybrid structures. The correct symbol is the delocalized by cloud as hexagon with a circle, as mentioned in fact 4. Because of these resonance structures, benzene has high stabilization resonance energy equal to 36 kilocalorie per mole. Take any double bond, you need 36 kilocalorie per mole. This is a high energy, so the reaction of benzene is not addition reaction, it is substitution reaction as mentioned in fact 1. Nomenclature of aromatic compounds. First, mono-substituted benzene means benzene with 1 substituent. Some mono-substituted benzene has common names like in benzene with methyl group called toluene, benzene with isopropyl group called commune, with a C double bond called styrene, with OH called phenol, anisole with OCH3, benzaldehyde as mentioned in slide 1, acetophenone, ketone with benzene, benzoic acid contain both aromatic and oxyl group with NH2 substituents, this derivative of benzene called aniline. The second type of mono-substituted benzenes that do not have common names: benzene if substituents bromo, chlorobenzene if substituents chloro, nitrobenzene, ethyl benzene, or propyl benzene. Di-substituted benzene, benzene with 2 substituents. There are 3 possibilities: either the 2 substituents on carbon 1 and carbon 2, this is called ortho, or 1,3 called meta, or 1,4 called Bara, for example, dichlorobenzene on carbon 1 and carbon 2 could be named as 1,2-dichlorobenzene or ortho-dichlorobenzene, while in the second example, chlor on carbon 1 and the second chlor on carbon 3 called 1,3-dichlorobenzene or meta, 1,4 could be named as 1,4-dichlorobenzene or bara. If the two substituents are different, use alphabetic order, as in example of bromochlorobenzene. Start with bromo, and since the two substituents are on carbon 1 and 2, it is ortho. So the name is orthobromochlorobenzene. For the second example, methyl substituents called toluene, so treat the compound as monosubstituted toluene nitro on carbon 3, so meta-nitrotoluene instead of meta-nitromethylbenzene. The third example, the two substituents, chloro and ethylene, ethylene with benzene called styrene, common name, so the compound is para because it is on carbon 1 and 4, para chlorostyrene. Benzene with the chloro and hydroxyl group with benzene called phenol, the two substituents on carbon 1 and 3, so it is metachlorophenol. Last example, the two substituents, amine and ethyl, amine with benzene called aniline, ethyl group on carbon number 2, so the compound name is orthoethylaniline. Polysubstituted benzene, benzene with more than two substituents. As in example 1, there are 3 methyl groups. Now choose clockwise or counterclockwise to give the first substituent the lower number, then the second as mentioned before. The compound is named as 1,2,4-trimethylbenzene. For the second example, there are 3 substituents, 1 methyl and 2 chloro. Give carbon number 1 for the methyl group because it is toluene, and this compound is disubstituted toluene. So the compound is named as 3,5-dichlorotoluene since the carbon bearing the methyl group is carbon number 1. For the last example, there are 4 substituents, one of them methyl, so methylbenzene is toluene. Now there are 3 nitro groups on carbon number 2, carbon number 4, and carbon number 6. This compound is 2,4,6-trinitrotoluene, which is TNT that used in explosions. In all previous cases, benzene is the parent. Sometimes you need to use the benzene as substituents rather than parent. To use benzene as substituent, it is called phenyl group. Phenyl group substituent, and benzene when it is the parent. While toluene is called as parent, if you need to use toluene as substituent, it is benzyl group. Phenyl group for benzene, benzyl group for toluene as substituents in both cases. The simple pH is sometimes used an abbreviation of phenyl group. For example, if benzene on carbon chain 1, 2, 3, 4, 5 carbons, you need to use benzene as substituents. It is phenyl on carbon 2, so 2-phenyl bentane chain is parent and benzene is substituents. If vice versa, it is 2-bentyl benzene. 2-bentyl benzene, 2-bentyl is substituent and benzene is the parent. For the second example, benzene and cyclopropane. If benzene is the parent, the name is cyclopropylbenzene. If cyclopropane is the parent, called phenyl cyclopropane. For the third example, there are 3 phenyl groups around benzene. The central benzene is the parent, and the 3 side benzenes are phenyl. And on position 1, 3, 5, so the name is 1, 3, 5 triphenyl benzene, phenyl for substituent benzene, and benzene is the parent. For the 2 benzenes bonded to each other, it is called biphenyl. This phenyl and the second phenyl, so biphenyl, the name of this compound. First example is nitrobenzyl alcohol, nitrobenzyl for toluene as substituent. The remarkable reaction of aromatic compounds is electrophilic aromatic substitution reaction. This reaction involves substitution of electrophile instead of one of the benzene hydrogens. Electrophilic aromatic substitution involves 2 steps reaction. One, addition of the electrophile, which is a slow reaction and need high energy to form carbocation intermediate. The carbocation intermediate then remove hydrogen to restore the resonance hybrid to restore the aromaticity of the benzene. This is called the mechanism of the electrophilic aromatic substitution reaction. The examples of electrophilic aromatic substitution reaction is 1. Halogenation, substitution with halogen, chlor or brom, chlorination or bromination. The reaction needs catalyst FeCl3. FeCl3 react with Cl2 to form Cl plus electrophile that attack the benzene and replace one of the hydrogens to form chlorobenzene or bromobenzene as an example of halogenation reactions. Second reaction, second substitution reaction is the nitration. Nitration, addition of nitro group. The reagent used for nitration is HNO3 in the presence of H2SO4. H2SO4 and HNO3 reacts to form NO2 electrophile that attack the benzene ring and form nitrobenzene. The third reaction is sulfonation, sulfonation of benzene. Sulfonation, the reagent used is H2SO4 in the presence of SO3 catalyst to form benzene sulfonic acid. The fourth type of electrophilic substitution reaction of aromatic compounds is Friedel-Crafts alkylation, and the fifth is Friedel-Crafts acylation. Alkylation means replace alkyl group instead of hydrogen, while Friedel-Crafts acylation replace acetyl group RCO double bond instead of one of the benzene hydrogens. Friedel-Crafts alkylation occurred in the presence of AlCl3 catalyst. AlCl3 react with alkyl chloride RCl. R could be alkyl group like methyl, ethyl, and so forth to form R plus. R plus is the electrophile that replace the hydrogen of the benzene to form alkyl benzene. While in the acylation process, acid chloride is used in the presence of AlCl3 catalyst to form the group, which is the electrophile that attack the benzene ring and replace the hydrogen by RCO acyl group substitution. Ring activating and ring deactivating substituents. Compared with benzene, substituted benzene could be more active than benzene or less active. Toluene and phenol are more reactive than benzene. The substituent is activating group, while for those less reactive than the benzene, the substituent is ring deactivated group. For example, chlorobenzene is less reactive than benzene toward electrophilic substitution reaction, and nitrobenzene is far less reactive than benzene. Chloride and nitro groups are deactivating groups, deactivate the ring toward electrophilic substitution reaction. While on the other hand, methyl group in toluene activate the ring, and the electrophilic substitution reaction for toluene is more reactive than compared with benzene. For phenol, it's more reactive, far more reactive than benzene. The rate of electrophilic substitution reaction for phenols 1,000 times more reactive than benzene. While methyl group, it is activating group, methyl group and hydroxy group are examples of activating groups, activating substituents. Activating groups are groups that donate electrons to the benzene ring, like methyl and the hydroxy group, while deactivating groups are electron withdrawing groups. They have high electronegativity and attract the electron of benzene toward itself. Activating groups or activators are amino group, hydroxyl group as shown in the table in slide 12, OCH3 and CH3 and phenyl, while the deactivating groups or deactivators are those groups to the left of the arrow, like NO2, SO3H, and other examples. The deactivator are less reactive toward electrophilic substitution reaction than benzene, while activators are more reactive than the benzene. This is the first difference between substituents. The second difference is the orientation. Orientation means where is the substitution will occur. All activator groups are ortho-para director, means the substitution goes to ortho and para directions, while the deactivators classified to two types of orientations. All deactivator except halides are meta director. Halides are deactivators, but the orientation is ortho and para director. The directing effect is important in the synthesis of organic compounds. For example, if someone needs to prepare bromo, nitro, benzene, ortho, and para, the process needs two fusion process, bromination and nitration. What is the sequence? But the sequence should be bromination first, then nitration, because bromo group is ortho and para director. The nitration goes to ortho and para direction. While if we start with nitration first, nitro group is meta director. To prepare ortho or para, you need to perform bromination first, then nitration. While in the synthesis of meta-bromo-nitrobenzene, you need to perform nitration before bromination because nitro group is meta director. Fused polycyclic aromatic hydrocarbons contain more than two benzene ring fused. In the first example, naphthalene, two fused benzene rings. The melting point is 80 degrees centigrade. The second example is anthracene. Anthracene composed of three fused benzene rings. The melting point 217 degrees centigrade. The melting point of anthracene is more than naphthalene. The reason is the number of carbon. As the number of carbon increased, the melting point increased. In the third example, phenanthrene. Phenanthrene composed of three fused rings but with branching. Phenanthrene is less melting point than anthracene. The reason is the branching. Anthracene is one chain, while phenanthrene, even though composed of three benzene rings but with branching, the branching decrease the melting point as mentioned before. For pyrene, composed of four benzene rings, fused benzene rings, the melting point increased as the number of carbon increased. This is the reason why pyrene has melting point higher than anthracene and phenanthrene.